Testing. 1, 2, 3. Right. So we're good. What we stopped last time was at the Trapezoid Rule. And so in this section, pretty much we use the summation or just the approximation for the integral. And the midpoint, obviously, we use all the midpoints. The trapezoid rule, we use not using the midpoint, but we use the endpoints and forming the trapezoid. Notice that when we have a bunch of trapezoid back to back like this, those two overlap. So those functions evaluate twice. That's why when we put together, remember, one on the edge, and then everything in the middle are overlap. So we're going to have two of those. And then at the end we have delta x divided by 2. Delta x, as always, is the width. Right. And then we did some example. Right, now we're on number 3, the Simpsons Rule. Right. I don't know what. Suppose the function is defined. I'm just going to write it out first, and then we explain later. Right. So if we use the Simpsons rule for n subinterval, left endpoint 4 times, and then 2, sorry. Right, so what we have in terms of coefficient is R 1, 4, 2, 4, 2, 4, 2, 4, 2, and then 4, 1. Right, where's that come about? I'll explain in a minute. Right, first of all, where n has to be even. And the width and the x and the sample points are the same. Right. So pretty much that. Notice the coefficient is 1, 4, 2, 4, 2, 4, 2. So how that come about? Sorry, I need to change the ink on the red one. So here what we have. So we have an interval, and we do this a lot. Let's say from A to B, for example. And we try to estimate the area under the curve. Let's say the curve goes like this. Try to estimate the area under the curve. This area. What we did earlier was we used the midpoint, or we used the trapezoid rule. But notice that, let's look at the trapezoid rule earlier. Even when we use the diagonal and the line, there's still the, if you look extremely close, there's the difference between the function and the line, namely this area. So usually what we're trying to do is try to use a line to approximate the curve, and usually that's not a good approximation. So what we do instead is we use a curve, estimate a curve. So what we do is still doing this, but what we try is, instead of trying to draw the diagonal here, what we do is we're trying to draw a parabola, go through those 2 points. A parabola would be a lot better approximation, because that the parabola can change the shape and try to fix into the curve here. And then next here, and then we may fix another parabola. The thing is, the parabola, we're not using this, not the vertex. What I'm trying to do is I draw the parabola in general like this, and I try to fit in what part of the parabola will be closest to the curve. It could be like this too. I mean, I'll just rotate it and change it so that will fix. I mean, not rotate like this, because the parabola have to be vertical, but what I mean is the parabola like this, or could be very skinny. So there are a lot of different parts of the parabola that we can fit into the curve to have the better approximation. So here we can actually use the parabola that open down. So that's the idea. So it should be better than the straight line. I mean, right. So bottom line is when we do use approximation using the Simpsons rule, what we have is, if we take in the point A is x0, x1, x2, x3, and so on. Actually, we try to fix this into the problem, but anyway, the coefficient will be 1, 4, 1 for the first parabola, and then the next one we have 1, 4, and 1. So that is one parabola, and this is another parabola. And so the coefficient pretty much is 1, 4, 1, 1, 4, 1, 1, 4, 1. And then when we add all of them up, naturally we will have 1 from the beginning, but and then 4, and then the 1 and 1 here overlapping. That's why we have a 2. And then there's the 1 overlapping. And then at the end it's going to be 4 and 1. So it's going to be like that. Right. Before we go no further, it's worth to say that in general, right, I think that is obviously a typo, so let me look it up. At least I have the book here. Sorry. I forgot the 2 there. It can be shown that s of 2n equal 4 t times 2n minus t to the n over 3. Right. One thing we need to know that the coefficients for 1, 4, 2, 4, 2, 4, 2, and then 4, 1. But here we have is the delta x over 3. Don't forget that we're going to have the delta x over 3. Right. Let's look at the first example. Find the Simpsons rule. Approximation. To the integral 0 to 1 sine of pi x using 6 interval. Sub interval. Right. Remember, whatever we use have to be an even number. Just want to have to be an even number of interval. So that's even, which is good. Right. So first I'm going to write down the interval. From 0 to 1. 1, 2, 3, 4, 5, and 6. Right. So there's 6 sub-interval, and the width always delta x is b minus a over n. So we have n is 6 going from 0 to 1. So 1 minus 0 divided by 6. So it's 1 over 6. So we have 1 over 6. And then 2 over 6, which is 1/3. 3 over 6, 1/2. 4 over 6, 2/3. And 5 over 6. We don't even have to reduce this. So those are the points. And then next we will assign the coefficients. Because when we did this, when we use the calculator, we will store that into a list. 0, 1, 6, 1/3, 1/2, 2/3, 5, 6, and 1. Store this into the first list. Next, the coefficient associated to this. The coefficient for the Simpsons rule is start with 1 and we're going to end with 1. So 1, 4, 2 should be 1, 4, 1, but the middle will overlap. So 1, 4, 2, and then 4, 2, and then 4, 1. So those are the coefficients that corresponding to it. So we store the coefficient 1, 4, 2, 4, 2, 4, and 1. Store that into L, the list 2. And then if we let the function equal to sine of pi x, and y1 is equal to sine of pi x, then next we will say evaluate y1 at L1, evaluate the function at this point, and then we multiply with everything on the list of L2, and finally we do the summation of that, and notice that in here we will multiply by delta x divided by 3. Right. So second parentheses, and we just enter this number 0, 1 over 6, 2 over 6, 3 over 6 is 1/2, 2/3, 5 over 6, and then 1. With that, we store into list 1. So we have that. Next, we store this coefficient into list 2. Right. 1, 4, 2, 4, 2, 4, 1, and close, and then store into list 2. Right. If we actually want to see a list, hit stat and then enter. Now we see we have the list like that, which is good. We can enter the number directly on the list like this. Once again, stat, edit, hit enter, and we'll just keep doing that. Enter the numbers here. Right. Next, the function y equal to sine pi x, but make sure that it is in the radian mode. So radian mode, which is good. Enter the function sine pi x. Right. That's good. Now, next, evaluate the function at these sample points. Alpha, trace, y1. Evaluate at this one times this 2. Right, so we have that. And then we're going to add all of this up. Multiply by delta x, divide by 3. Right. So add all of this up. Second stat. Go to math. Option number 5. And then I just go here. Highlight that. Hit enter. So copy and paste. And then times delta x is 1 over 6. And then divide by 3. So we do that, we have 0.637. So it is simple enough, right? Again, coefficient 1, 4, 2, 4, 2, 4, 2, and then 4, 1. The reason of the 2 because of actually it's just 1, 4, 1, and just keep repeating 1, 4, 1, 1, 4, 1, and just keep doing that. Right. I guess we can do one more example. Right, now we're using this for 4 subintervals, and once again it has to be even. So, right, now from 0 to 2. The first thing we do, of course, is the width. We go from 0 to 2, so 2 minus 0, and 4 subinterval, so that is 0.5. Right, so we have 0, 0.5, 1, 1.5, and 2. So those are the sample points. And then the coefficient will be 1, 4, and then the overlapping 2, 4, and 1. Those are the coefficients. If it is the trapezoid rule, will be 1, everything 2 in the middle, and then 1. Those are the coefficients. Right. So pretty much we store 0, 0.5, 1, 1.5, 2, store until this one. And then the coefficients 1, 4, 2, 4, 1. Store to list 2. And then evaluate the function at list 1 times list 2. So a nice thing about when we write this is multiply point-wise, meaning they calculate f of 0 and then times 1, f of 0.5 and then times 4. They do that point-wise. So that's why the list have to be corresponding like this. And then finally, we take the summation of all of that. Answer would be whatever we have here multiplied by, notice that in here it is delta x divided by 3. Right. So first enter the function e to the x squared. I use this a lot because this function we cannot integrate using the function that we know. Right, so we do that. Enter the function. Enter the list. So second parentheses 0, 0.5, 1, and 2. So 1.5 and 2. Start to list 1. And then list 2, 1, 4, 2, 4, 1. Close the parentheses, second parentheses. Store this into list 2. By the way, we can, as mentioned before, we can always hit the stat, edit, and then we can change the numbers here. If we want to clear a list, highlight the list, hit clear, and then enter. And then we enter 1, 4, 2, 4, 1. So we can enter the list directly into here. And then when we highlight the list, just clear and then enter. That will do it. Right. And then we have evaluate this. Alpha trace that y1 evaluate at list 1 times list 2. Right. And then add all of them up. Second stat, go to math, option number 5, and then go here, highlight, close that, and then times delta x, 0.5 divided by 3. Usually this is an approximation. We might want to math, go to option number 9 here. Just integrate and see how good the approximation is. E x squared dx. Right. You see, that's not a very good approximation, but that to be understandable because the Simpsons rule, we use the parabola to approximate. We have an exponential function, not just exponential, any exponential function. This one will go to infinity very fast. So using the straight line, or the parabola or anything like that. It's not a very good approximation. Right. Talking about the error. For theorem. Right. Now this is very long, but we still need to write that down. So errors for midpoint and trapezoid rule. We put those two together because both of this we use the straight line to estimate the curve. The Simpsons rule, we use the quadratic or the parabola to estimate the curve. And then of course we can use higher degree as well. But let's write this down. So assume the second derivative exists. Not only exists, it has to be continuous. On the interval AB, and K is just a real number. Is a number such that the second derivative less than K for all x in AB. The absolute error in approximating the integral from A to B using midpoint rule. And trapezoid rule. Or the error using the midpoint rule will be less than or equal to K B minus A divided by 24 times delta x squared. And using the trapezoid rule, be less than or equal to K times B minus A over 12. So first thing, when we look at this, this is divided by 24, this is divided by 12, divided by 24 will be the smaller number, right? So this is a better approximation because the error is smaller. And then the delta x square, meaning that the smaller the interval that we choose, we're going to square that. So that is depends on the square of delta x. Right. B. Error using Simpsons rule. assume the fourth derivative exists and is continuous. Usually which is continuous is good enough already. We don't need exists, because if it is continuous, it certainly exists on the interval a and b. Just that. The fourth derivative less than k for all x in AB. Then the error in approximation of the integral from a to b fx dx using Simpsons Rule is using Simpsons Rule with n subinterval is the error using Simpsons Rule less than or equal to k b minus a divided by 180. So divided by 180 is even smaller, and delta x to the fourth power. So the comparison with all of this, when all things are equal, the delta x is very small. Usually to the fourth power is a lot smaller than to the square. So this error is the best of all of this. I think we look at one example and see how it works. Example. Use now we just find the error. Don't need to find the values. Find the absolute error using Simpsons Rule. With 16 subinterval to approximate this integral from 0 to 1 of e to the x dx. Right, so of course the formula is there, but let's just find all the components. First, obviously the function is e to the x. The reason I choose e to the x because in here we're required to take the fourth derivative. So the nice thing about this is the function e to the x derivative will be the same. Doesn't matter how many times you take it, the fourth derivative is still the same. Right, that's why I choose e to the x. Next, we have to find the maximum of this function. Now, e to the x, what's that look like? E to the x look like that, right? From 0 to 1. So obviously e to the x is an increasing function, so the maximum of f of x is increasing, so the maximum will be at the endpoint on the right. The maximum is equal to whatever at the endpoint, which is e to the first. If the function goes like this, the maximum is at the endpoint. So we say the fourth derivative is maximized at x equal to 1, and because of that it is going to be less than or equal to e. Which is about 2.71828, and we're going to let k equal to that number. Just to be just make to absolutely sure, we can always choose like 2.72, slightly bigger than this, or we can choose 3. It doesn't matter. K, remember, it's just a number that is bigger than all the fourth derivative. The fourth derivative going like this, the maximum is at that point. We just choose something slightly bigger than it, 2.72. That will be enough. So that is k. Choose a number that is bigger than any fourth derivative from 0 to 1, and that is 2.72. And the rest is easy. Delta x, as always, b minus a over n, b minus a over n. And then we have everything just put in that formula. So the absolute error using Simpsons Rule be less than or equal to k times b minus a over 180 delta x to the fourth power, k 2.72, b minus a over 180 delta x 1 over 16 to the fourth power. So we have a fraction, we have a fraction k 2.72 times 1, that pretty much, we don't even need that, divide by 180 times another fraction of 1 over 16 to the fourth power. So we have 2.3 1 times 10 to the negative 7, meaning that the error using the Simpsons rule will not be more than this. This is the maximum absolute error using the Simpsons rule. So if we use the Simpsons rule using 16 sub-interval from 0 to 1 for that function, the error cannot be more than that. This is the worst case scenarios. We have that error. Right, so that's nice and all, but what do you really need for this section? Not that. Let me summarize everything. This one. So we have the midpoint, right? So what was that, number 4? So let's try number 5, summary. To approximate the integral from a to b using n subinterval. This is all we need to know. The midpoint rule using n rectangles is equal to how do we write this? F of x naught, f of x2, 1 times delta x. So that's the midpoint. Scratch that, sorry, the midpoint actually. Let me do that again. Right, the midpoint rule. Right, so we use the midpoint, and I apologize that the midpoint have to be this. The average of that, and then the average of x1 and x2. On the way to xn minus 1 plus xn divided by 2 times delta x. Right, should be that. Of course, usually for the midpoint rule, it's better just draw a line and then find all the midpoint manually, unless we have like 100 points. That's different story. Right, trapezoid rule. We have just x naught and then 2 for everything in the middle, and 1 at the end, both ends, delta x divided by 2. And then the Simpsons rule be 1, 4, 2, and then 4, and then back to 1, and then delta x divided by 3. Right, so that is the Simpsons rule. The only thing different from those two is in here n has to be even. Simpsons rule only works for the even number of points. Right. Of course, there are a lot more than this, but though still we use a linear function, a straight line, and here we use quadratic function to approximate. So that pretty much that much we need to know for the Simpsons rule. The error estimate for that we really don't need it. Right. With that, we go back to integral. Slightly different is improper integral. Right. I need to switch a few things around. Now we don't need the calculator as much. So let's do that. To be perfect balance. Come on. Wrong one. Sorry, I need to just move things around here. I will go to section 8.9. Oops, wrong one. Right, that better. 8.9. Right. Section 8.9, improper integral. Before we go to the first part, what we have here is an integral. Right. What makes this one improper is the limit might be a problem, or the function may be a problem. This one may be improper because due to either A or B is infinite limit. Number one, A and B are infinite limit. In particular, meaning that A equal to negative infinity or B equal to infinity, maybe both, either that or the function is undefined. It is undefined at any point from A to B. At a point on A and B. So, for example, it's normal to find the area under the curve, which is easy from A to B. Now, if we find the area under the curve to infinity, then that is improper. Either that, or we might have the case where the function is undefined. And we're trying to find the area where the function is undefined here. So, two things that make this improper. The first one is because of the infinite intervals, one of the endpoints are infinity. And the second case where we have the function is undefined at any point in the middle. So the first reason is improper integral is because of infinite intervals. The endpoints, one of the endpoints is equal to infinity. Right, so we have three scenarios here. The first one, the upper bound is infinity. The second one, the lower, is negative infinity. And we might have both of them. Right. Actually, let's take a 5-minute break here until we continue. We continue at 9:06. By the way, I posted the review for the second test, and according to plan, if everything up to the pace that I plan, we should be able to finish everything for the test by Wednesday, by next Wednesday. So right, we continue. If the function is continuous on the interval from a to b, from a to infinity, then integral from a to infinity, one of them is infinity, that make it improper. So what we do is simply replace the infinity here by the limit by b, and then take that limit go to infinity, and in that case we still go from a to b. So pretty much just replace infinity with a letter and then take that letter go to infinity. What we actually do first is we do this first and then we take the limit. Right. And of course the limit has to exist. We define one more thing later, but for now let's define for the other cases. This time if we have negative infinity at the lower limit, go to B. The letter not really important here, but usually whenever possible we use A to be the lower limit. Of course, it works if the limit exists. Now what happens if both of them are infinity? In that case, easy. Just chop that somewhere in the middle and combine these two. Right, now we have both from negative infinity to infinity. F of x dx equal to, now we're going to use both. From A to some number between A and B. Then plus limit we go from C to be f of x dx, and of course the limit must exist, both of them. So both the limits exist, and C is any number between A and B, any real numbers between negative infinity to infinity. So, right, most importantly, when we define this thing, we have some terminology here. If the integral, if the limit exists, it is said to be convergent. Otherwise, it's said to be divergent. Like those limit exists, the integral, the improper integral, is said to be convergent. And if it does not exist, be divergent. If limit does not exist, it's said to be divergent. Right, so that's all of the definition and terminology. Before we actually do some example, I just want to review a few things. because we use this a lot. Polynomial is usually easier to do, but if we have the exponential function, exponential function, exponential function is positive above the x-axis, but what we focus here is on the right end when a to something that goes to infinity is going to infinity. On this end, a goes to negative infinity is equal to 0. That's exponential function. And then we have log. On the right hand side, log of something that goes to infinity is infinity, and log of something that goes to 0 on the right hand side is negative infinity. So we need to know this when we have those scenarios. Right. Other than that, let's just go to the first example to see what happened. Right. Before we go to the first example, here's the idea. Let's say we talk about the area from 0 to infinity, and you say if we go like this, obviously the area is infinity, right? Of course, I would agree. In that case, the area goes to infinity. Now, if the function like this, then is this area finite? Of course, actually we don't know that. Depends on how fast it goes to 0. It could be like that, or could be extremely flat. We don't know that. Depends on the function. Sometimes the area here is infinity, sometimes the area is a finite number. So that's why we have to work on different scenarios here. Evaluate. So we have that. So obviously it is improper integral. So first thing we say, the problem is at infinity here. So we have to fix that. And we just state upper limit. Let's use b for upper limit. Now we use b instead of infinity. When I took calculus 2, I really hate to do that. I said, why don't we just skip infinity and use infinity? Well, there's the reason we're doing this. Because after all, we do this integral first, and then we find the limit. That's the point. Right? So we're going to do this integral first and then find the limit for b. So we have to have something there to find the limit later. Right. So, by the way, we did a bunch of this, right? What is an integral of e to negative 3x? Is e to the negative 3x. The same thing divided by negative 3. Right? We did this many times in the iteration by parts. Limit will go from 0 to b. Right. Now put in the limits. Sorry, that could be confusing. By the put in the limit, I mean 0 and b, not that. E negative 3b over 3 negative 3. Subtract e to negative 3 times 0 divided by negative 3. Right, let's simplify this. That is negative 1 over 3 e negative 3b negative and negative, that's a plus. Right? Now, what happened? E to 0 power, go back to the previous note. It's worth to also say that e to the 0 power is 1. Same token, ln of 1 equal to 0. Right. So we know what happened in the limits at the endpoints, what happened in the middle. Same thing for that. Right. So e to 0 power is 1. Now what happened if we put infinity in here? So what is e to the negative 3 times infinity if we put infinity in here? Right. E to negative infinity, well, that's why we did this first. When the exponential function goes to negative infinity, that's 1 equal to 0. Oops. So the whole thing here go to 0. Bottom line is we have negative 1 over 3 times 0 plus 1 over 3 times 1. So this is 1 over 3. Right? So all of that, the area under the curve of e to negative 3x, the area is equal to 1/3. It is finite. Because it is a finite number, we say this is convergent. Try another one. By the way, I'm going to skip this one. And we'll do that later. Consider f of x equal to 1 over x to the p power. Evaluate from 1 to infinity of f of x for p greater than 1, p equal to 1, and for p less than 1. We'll do 3 problems. So the first one, for p bigger than 1. Right? So integral from 1 to infinity of 1 over x p dx. Right, so this is actually fairly simple integral, but the first thing we do is don't jump into it. Take care of the limit first. Upper limit, so let's use b. Right. So change the limit. That's the first thing we do. By the way, to integrate this, it's much better to use the power rule. So write this, move x to the p from the bottom to the top to x to negative p dx. Now, x to negative p, integral will be x to negative p plus 1 divided by negative p plus 1. Just standard power rule, going from 1 to p, 1 to b. Right. Notice that when p is bigger than 1, how do I do this? Now let's make it minus p on both sides. From here, we will have 0 greater than minus p plus 1. Right, so when p bigger than 1, equivalently negative p plus 1 is negative. So meaning that this power here is negative power. And then we're just going to put b in for x. So I will write 1 over negative p plus 1 b to negative p plus 1, and then minus 1 over negative p plus 1 times 1 to the negative p plus 1. In fact, let me just write this again because I'm running out of space. Right. 1 over negative p plus 1 times b to the negative p plus 1, subtract 1 over negative p plus 1 times 1 to the negative p plus 1. Right. Now to make it a little more complicated with the constant p, but remember p is a constant. Right, now, so this what not complicated is this one. 1 raised to any power is 1. and so that one, it doesn't matter, right? Now the question is, what is this? Think about it. If we have infinity raised to a negative power, let's say negative n, when n is positive, what's that? Because when we write this, we can say 1 over infinity to the n power, right? When n is positive, 1 over infinity is equal to 0. So bottom line is, if we have infinity raised to a negative power, it's going to be 0. So that one goes to 0. So bottom, when everything, so this one goes to 0, and so this limit equal to negative 1 over negative p plus 1. And because we can say it, move the negative down, p minus 1, and that is convergent. Because it is equal to a number, so it is convergent. Now what happened for p equal to 1? For p equal to 1, we just have 1 here, right? Regardless of it, first thing we do is, of course, changing the limit. Upper limit, so we use b. Right. Integral 1 over x. Is ln of x. Don't forget there's a limit from 1 to b. Right. Then put b in and put 1 in. And then we take the limit. Put b in for x and put 1 in for x. Right. Now ln of 1, ln of 1 is 0. Even. Of course, if you're not sure about that, put in the calculator. Right. And what is ln of infinity? Well, the ln function, or like this. So ln of something goes to infinity is equal to infinity. So that one goes to infinity. Bottom line is this limit equal to infinity. If it is equal to infinity, not a finite number, or the limit does not exist, we say this one is divergent. Right. So it's not that bad, right? So integrate. Just have the limit to worry about. But other than that, like I said, it will be a little bit more difficult when we do this for a particular p, for the general p values. But when we have a particular number, it will be a lot easier to do. Right, case number 3. For p less than 1. If p is less than 1, subtract 1 on both sides. P minus 1 is negative. Actually, it is correct, but we might not even need to do that first. Right. Keep that in the back pocket, actually. Right. Still doing this. So, before we do anything, have to change the limits. Upper limit, let that be b. And this we can rewrite as x to negative p dx. Right, so actually it will work out the same way as this. Integral negative p plus 1 over negative p plus 1. 1 from 1 to b. Right. When put b in here, put 1 in here. On the homework, you don't have to worry about the p here. In the homework, you have a particular like 2 or 1/2 or something like that. So put in b and put in 1. Now, what is this? So this is minus p plus 1, right? So I actually have to minus p on both sides. So what we have here is negative p plus 1 is positive. If that is the case, we have infinity raised to a positive power is obviously go to infinity. So this one goes to infinity and this one is positive. So bottom line, what we actually have is 1 over that is positive. That's all we know. Some positive number times infinity minus 1 over a positive number. 1 raised to any power is still 1. Bottom line is it is equal to infinity, which is divergent. So bottom line is the 3 scenarios. P is less than greater than 1. I'll let you. So when P is less than 1, that is convergent. If P is greater than 1. When P is greater than 1, it is convergent. For the other 2 cases, P equal to 1, divergent, less than 1, divergent. So we say divergent if P less than or equal to 1. So convergent if P greater than 1, divergent if P less than 1. So that including like 1/2, 1/3, or anything like that. It will be infinity and will be divergent. And if it is bigger than 1, it will be convergent. So if we look at the graph here, we have a bunch of different functions. So if it is close enough, it go to infinity, it go to 0 fast enough, it will be convergent. Other than that, it will be divergent. So that's what we have. Convergent if it is greater than 1, otherwise divergent. The example in homework will be easier. We might have like 1 over x squared or 1 over square root of x. In that case, it's 1/2. So let's just look at this real quick. Let's see, what do we have here? From 1 to infinity. 2 is bigger than 1. So this equal to 1 over 2 minus 1. Because 2 is bigger than 1. Because p is equal to 2, which is bigger than 1. Now, if we have something like 1 over square root of x instead, or we rise to the 1/2 power, since p is equal to 1/2, which is less than 1, so this one is divergent. Yeah. So in the homework, actually you might have to work it out, but it can be shown. We just show in general, if it's bigger than 1, it will be convergent, and there's the values for that, equal to 1 over p minus 1. If it is bigger than 1. If it is less than 1, it will be divergent. There's no values for it. Right. More samples. 4. Right. Before we do anything, the first thing when we see the limit on the integrals, have to change that. This is a lower limit, so we let that be a. I'll just do that. This being integral I. Right, so how do we do that? Right, first, let me just copy that. First, how do we integrate this? The two things we might use: integration by parts or substitution. Right. The reason that we have to use substitution because nobody can integrate this. So we have to let u equal to negative x squared. And then we take derivative. negative x squared derivative is negative 2x. Move the dx over. And then divide by the dx. So we solve for dx. Also, we have the limits. When x equal to 0, u equal to negative 0 square, just 0. When x equal to a, u equal to negative a square. Right. Now we can substitute into this integral. Still have the limits. Right. Now, instead of go from a to 0 for x, we go from negative a square to 0 for u. For x, a negative x squared is u. Dx is this. Sorry, this. Cancel the x. Take out the 4 on the top. Negative 2 at the bottom. 4 on top, negative 2 at the bottom. Negative a squared, 0, and just e to the u, du. Right, so now it's bad. 4 over negative 2, negative 2. Integral of e to the u is just e to the u, right? Go from negative a squared to 0. Put in 0. And then put in a square. Right. Now, e to 0 power is 1. So we just have negative 2. Negative and negative, that's plus 2. E to negative a square. Right. Now just need to determine what is that. E to negative a square. So think about this. E to the negative infinity square. What's that? Negative infinity square is still infinity. Negative infinity square is infinity, and we have negative infinity. And e to negative infinity, well, that go to 0, right? So that term go to 0. So this equal to negative 2. Right. Is there a way to confirm this? right. We cannot really put negative infinity here. Let's say we try negative. That I think is small enough. And then we have 4x e to the negative x squared. Right. This should be close to negative 2, if not exactly negative 2. Wait. Maybe that's too negative. I'm not sure what method they use, but that is too negative. Maybe even that is good enough. Negative 2. Right. Why is that? Because if we graph the function 4x e to the negative x squared it will go to 0 rather quickly, so we don't even have to go to negative 9999. That would be too much. We just need to go from 0 to 99 or something. I guess because you know the why this is equal to 0 when we have too big number, because after all the calculator what the calculator use is the Simpsons Rule or the midpoint or the trapezoid. Actually I think they use something with the higher degree than that. So let's say Simpsons Rule. For Simpsons Rule, calculator have to choose some number of points. I say they choose 100 points or something like that. It would not be enough, because if we have from negative 9999 and 0, if they use 100 points, then the point is not even close to 0, so all of them have the 0 values, so that's why it's equal to 0. So instead, if we go from negative 9 to 0 and we choose 100 points, then we have some point that is actually close to 0. Remember, because the function will go to 0 rather quickly, if we choose a bunch of points here, all of this are equal to 0 anyway, because that go to 0 very fast. So we have to choose something like negative 9 or negative 99. How about negative 999? It get close to 0. So by the way, yeah, that is the good choice. However, as mentioned before, this one go to infinity very fast. If we choose e to the negative 99 as negative infinity, it just only evaluates the point here and give us 0, which would be wrong. So in that case, the point here is we're trying to find the limit of this. So in that case, negative 9, if we put the too big of the numbers there, it will be wrong, because this is not that we did anything wrong or the calculator did anything wrong, just because the function go to 0 too fast. And if we emphasize the negative 999, that will be 0. Think about this way. If we have to calculate the area, something like this, most of the values of the area will based on the values close to 0 and not the values that close to here. So we can choose 1,000 points more on this side. The area here is too small compared to what we have here. So that's why when we can set it go to infinity, it doesn't matter. What it actually matters is only this part. The part after that is way too small to consider. And that's why we have to do this by hand and have the better picture. Right. We cannot do that. What I do is, instead, I combine this number 5 prompt with the number 2 that we skipped earlier, and we put them together into this prompt, negative infinity to infinity of 1 over x squared plus 1, x squared plus 1 dx. Alright, I combine both of them into this prompt. Yes, in general, e to the 99, I mean, not 10 to the negative 99 or 10 to negative 99 will be positive and negative infinity. But in this case, because of the calculation error, it might not be a good choice. If there's an option to set up the calculator using 10,000 points or use a bunch of points, then yeah, you can use that infinity, but won't be able to do that. Alright, now let me ask you this. Why do we have to change the prompt to here instead of x plus 1 over there? Right. The reason we have to do that, because if we just have this one is undefined at x equal to negative 1. So we cannot do this. We cannot do that prompt because there's an undefined. That is the second part of the improper integral, where we have something that is undefined in the middle. Cannot do that yet. Alright. So when we do this, first thing we do is, if both of them are infinity, have to split. How about we split from negative infinity to 0? We can split it anywhere in the middle, but I choose 0. Right. Now, how do we do this? Now, before we worry about the integral, let's first change the limit. Negative infinity here, lower limit. Let that be a. And infinity is the upper limit. Let that be b. Since both of those integrals are the same, now let's just focus on the indefinite integral. Let's drop the limit. Just integrate. Right. How do we do this? So, this is section 8.4 Trigonometric Substitution, where we have a square and a square so we use trig substitution, a variable square plus a constant square, so that is a tangent. So let x be tangent of theta. So derivative is secant square, move the d theta, by the way, on the test review for this trig substitution problem, you just need to write the problem in terms of theta, and that will be good enough. I will not ask you to do a complete problem. You see. Right, and then the part here, x squared plus 1 square, or just 1. X is tangent theta plus 1 is tangent square plus 1, which is secant square. Or we say secant. Just secant square, that's good enough. So the integral equal to 1 over x squared plus 1, that is secant square. Dx is that. Just have this, and integral of that just theta plus c. So what is theta? If we have x equal to tangent theta, then if we want to solve for theta, is tangent inverse of x. So this equal to tangent inverse of x. Right, now back to our problem. The problem of limit we did the integral, give us tangent inverse of x. So here we just have that equal to limit a to negative infinity, and that is tangent inverse of x going from a to 0. And that tangent inverse of x going from 0 to b. Right? Now, we have limit of a go to negative infinity, tangent inverse of 0 minus tangent inverse of a plus limit b goes to infinity, tangent inverse of b minus tangent inverse of 0. Right, so what do we have here? So what is the tangent inverse look like? it look like that. Doesn't help much, but the tangent inverse look like this. Obviously, tangent of inverse of 0 is 0. But what will be the values that will go to infinity and the values that it goes to negative infinity? Well, this is pi over 2 and negative pi over 2. Those are the asymptotes of the tangent inverse. So when we put it back into our problem, we have 0 minus this one negative infinity will go to negative pi over 2, and this one go to pi over 2. So 0 minus negative pi over 2 plus pi over 2 minus 0. And when we do that, pi over 2 is equal to pi. Let's take a 5-minute break. When we come back, we continue the second part of the improper integral. This time, due to the function is undefined. Right. Continue at 10:11. Because the secant square and secant square cancel out, and we just have 1 here, right? Integral of dx is equal to x plus c, right? Same thing. This is integral of theta d theta, and that turned into tangent inverse. Oh, that turned into theta first, and then since x equal to tangent theta equal to tangent inverse of x. What we did was x equal to tangent theta. I take the tangent inverse, and tangent inverse and tangent cancel out. That's what we end up with. So of course the secant square do not go to equal to tangent inverse. It is because it cancel with the secant square in dx, and that cancel out, and that gives us theta, which is tangent inverse. I should zoom out. Right, I will continue. Right. The second part of this is the improper integral because of the unbound integrals or because of the functions undefined, loosely speaking. So now we just focus on the definition we have here. I'm trying to highlight. We have the case where we have it is continuous on the interval, continuous on the B side, but not continuous on the A side, or the other way around. Continuous on A, but not on B. And on next one, it is continuous on A and B, but there's some point in the middle that is not continuous. This is the case where we talked earlier. For this function, if we have to do it, there's a problem at -1. So we cannot do that conventionally. Alright, so let's write out these three scenarios, three cases. Is everything's okay? It buffer during the break, right? This say set drop about this. Yes, it is about 40 seconds worth of frames that we lost. Sorry about that. I think it during the break, so it should be fine. Right, now if there's a problem at A, replace that with the limit. So think about this. If we go from A to B, and it's said to be a problem at A, on B is fine, but the problem is A, meaning that on the right side of A, it is okay. Don't care about what happened on the left. So in this case, we will replace the A with another number. I said, why don't we just write A plus, right? Yeah, but no. Replace that with C, if that is a problem. And it works if the limit exists. Right, so if there's a problem on the left hand side, now what happens if we have the problem with the right hand side? With the limit x go to b from the negative side, equal to plus or minus infinity, then at A is okay, but at B there's a parentheses. So obviously it only works, we only need it to work if it goes from B from the right hand side, from the left side, so it's negative side. Don't care what happened on the other side. So if it is the problem, change that to something. We also use C. Okay. Provided the limit exists. Right. So if the limit is the problem, replace, if one of the upper or lower limit of an integral is a problem, remove that, put something else in it, and check the limit goes close to that point. Suppose f is continuous. On AB, except at one interior point. then we just need to split in both. If there's some problem in the middle, you just have to split from A to that point, and from that point to B. And not only that, of course, now this will replace into this, and that into this, into that, and that into that. So pretty much we have to split, and then both of this become those two. And of course, provided the limit exists. And then we have the divergent and convergent like we had before. If the limit exists, the integral is said to be convergent. By the way, in the next section, the next chapter, pretty much the whole chapter, we hear about this a lot more. That otherwise, the integral is divergent. Divergent if the limit does not exist. B. Ouch. Do we have an easier example than this? I guess we just have to deal with it. Make things easy, a little bit easier. To change one of them to 0, right? Change this to 0, so we don't have to complicate things. Go from 0 instead. Right. The first thing we say, what's wrong with that? It's perfectly fine, right? The integral is, yes, there's nothing wrong with that. The problem is when we put any numbers between 0 to 3, especially when we put 3 in here, 9 minus 3 squared is 0. Divided by 0 is undefined. So let me write that note. Is undefined. At x equal to -3, positive 3. So that's why I want to change the problem to 3, because there's a problem at both ends. So I have to take care of. Now just change to 0, So we have to worry about the 3 only. So if that's the problem at 3, what do we do? Of course, we'll replace that with the limit. Let's use c equal to 3. Right. Not only that, we go from 0, which is perfectly okay at 0. At 3, there's a problem at 3. So if we go from 0 to 3 in here, it is going to 3 from the right, from the left hand side only, right? So there's put the minus there, because we can only go to 3 from the left side. And here we go from 0 to c. By the way, if you do enough problem, this one is sine inverse. Right. Now let's look at the integral. Just the integral, indefinite integral, without the limits. Right. Of course, this is also a trig substitution, a constant square. Minus a variable square. So let x. So when we have this scenario, this case, section 8.4 says that we're going to say use trig substitution, and this scenario is a sine, so 3 sine theta. Take the derivative. A 3 cosine theta. Move the d theta. Right. Can substitute that in for the x. That will be later. Right. The 3 square minus x square. Square minus 3 square sine square theta. And that gives us 3 square cosine square. Right. Now we put that back into there. And the dx, that into dx. So the integral I becomes 1 over square root. By the way, for this one we can definitely write as 3 and cosine square. and then dx 3 cosine theta d theta. I will just substitute everything in, and if everything works out, it will take care by itself. Just keep that for now. Square root, cancel the square. Three cosine theta. 3 cosine theta. Well, that's convenient. The cosine cancel the cosine. 3 cancel the 3. So everything cancel out. We only left with pretty much 1. The integral will be theta plus c. Right. Now, we need to solve for theta. Go back to this problem. X equal to 3 sine theta. So sine theta is equal to x over 3. Taking the inverse, theta equal to sine inverse x over 3. So this integral is so the integral I is equal to sine inverse plus c. Right, so that's just the integral. Now we'll go back to the problem. Back to the limit. Now back to the integral. We still have the limit though. But the integral is going to be sine inverse, of x over 3. Sorry, that's what we have, and I forgot to write that. Right, so sine inverse of x over 3. And we evaluate from 0 to c. Now put 0 and c into it. And we have sine inverse of that minus sine inverse of 0 over 3. Now this should be easier if we use a calculator, and usually when I use the sine inverse or any trig inverse, it will be better if we use in degree mode, so we can tell what exactly it is. Right. So earlier we did have tangent inverse of a very big number. Right. Let's see if we can use that for infinity. That works. 90 degrees. Yeah. Now we'll try the same thing here. Sine inverse. Now we have 3 over. Don't know why I write like that, but that obviously is not true. Sorry. If we put 3 in here, sine inverse of 3 over 3. So what is sine inverse of? Practically 1. Right, 90 degrees, which is pi over 2. And what is sine inverse of 0? 0. So this equal to pi over 2 minus 0. Right. Right. Let's go to the next example. Right. Now, just like what we did earlier, we have to write out what is the problem with the function from 1 to 10. Right. From 1 to 10, the only problem is when x equal to 2, 2 minus 2 is 0, divided by 0 is undefined. So first, at x equal to 2, the function is undefined. If there's a problem at that point, we'll split to 2. Right, and even then it's not right. Normally we split at 2, so let me write out here. We want to integrate from 1 to 10, right? We know for sure 2 is the problem. So what we do is we have to split. Cannot take 2. Take anything on the left, anything on the right is okay, but cannot be 2. So in that case, we have to rewrite this as, take care of that limit, from 1 is going from 2 to the left. And from 2 to 10 is actually on the right side of 2. Because on here is on the right side, on here on the left side. Now, pretty much we have to do 2 problems. Let's this integral I1 and this I2. Right. So when we do the improper integral, make sure determine where the problem is. If it is in the middle, we have to split in two, on the plus sign, on the minus sign. Right, so first we do this. It's just simple power rule. So I will write x minus 2, sorry, to the negative 1/3 instead. So simple power rule. Right, just use simple substitution. Let u equal to x minus 2. In that case, derivative is 1, so du is equal to dx, and then changing the limits from 1 to c. When x equal to c, u equal to c minus 2, x equal to 1, u equal to 1 minus 2. So it is from negative 1 to c minus 2. Right. Put it back into this limit. X minus 2 u negative 1 over 3. Dx is du. So integrate is u to the 2 over 3 over 2 over 3. Where's the limit? Negative 1 c minus 2. Right. Divide by 2/3 is multiply reciprocal. Three halves. 2/3. 3 halves. It's just power rule, right? Negative 1/3 plus 1 is 2/3. Divide by 2/3. Flip that. 3 halves. And then we put in c minus 2. And then minus right. Finally, we put negative 2 in here for c. That gives us 0, right? 0 to the 2/3 is 0. And And what is negative 1 to the 2/3? It's positive 1. So we have three halves times 0 minus 3 half times 1. So it's minus 3 halves. So that's one of them. The first one. Now we'll do the second one. Right. So we see negative. Right. So we actually do this one exactly the same way. The only difference is the limits. The only difference is here. So still the same substitution. So the same thing. du is equal to dx. Now changing the limit. X equal to 10, u is 10 minus 2 is 8. X equal to c, u equal to c minus 2. C equal to 2 on the right side. 2 on the right side. The limits c minus 2 to 8. That is u. Dx is du. Right. The integral is the same way. U to the negative 1/3 plus 1 2/3 over 2/3 won't form c minus 2 to 8. Bottom line is we're going to flip the integral. Flip the denominator. And then put in the limits. Let's put in the numbers in here. 0 to the 2/3. Of course, it's equal to 0. So that equal to 0. Now what is 8 to the 2/3? is 4. So we end up with 3/2 times 4 minus 3/2 times 0. That gives us 6. And finally, the integral from 1 to 10 of 1 over x minus 2 to 1/3 dx is equal to the first integral plus the second. The first integral, negative 3/2 plus 6. So negative 3/2 plus 6, that's be 9/2. I'm curious to see if the calculator can do this. It takes a lot longer. Oh, yeah, close to 4.5. Yeah, and that's 4.5 with this 9/2. So yeah, so that's correct. But you see, it takes a lot longer than it need to, because the function is like this. And it calculates this area and then this area, and there's a lot of values that extremely big and extremely small, and that's why the calculator will take a lot longer time to evaluate. But fortunately it come out right. But like I said, sometimes I have to stick it, do it by hand. So if I ask you only half of it like this, it's not that bad. The problem here is when we have to do 2 of them at the same time, 2 of them, and then combine. Yeah, it's a little more complicated. But other than that, a problem like this is very typical, where we have one of the boundary is the problem. Replace that with the limit, and we just go ahead and do it. If there's a problem in the middle, cut it off, do it on the left and on the right. So I have this one. Right. Next, we have more example. But we won't be able to do this. Just want to show you real quick. Three. That will be enough to fit it in here. So we have a classic problem, very classic problem. I'm just going to draw it instead. That's my little, okay. So we have a function. We have the function 1 over x. And let this rotate about the x-axis. So what we when we rotate, we end up with and there's a lot of name for it. We won't be able to do this. But what the name for it is called the Panther paradox, or Gabriel horn, or Torricelli trumpet. So first of all, it looked like a trumpet. So they call the Torricelli is the guy that called it Torricelli trumpet. Makes perfect sense. The Gabriel horn. Gabriel is an angel, and the story says an angel will blow this horn. When we hear it, this is the end of the world. So that they call it the Gabriel horn. Don't worry about it. This go to infinity though, so take a long time to get there. Right. So there's a name for it. Oh, and where's the Panther paradox come from? Right. So actually, if you go on Wikipedia and search any of these three, it's very great story. But cool things about this is if we have this one and we rotate about the x-axis, what we have, of course, is the surface area of the horn and the volume inside, right? So surface area around and the volume inside. The nice thing about this, or the weird thing about this, is the volume is finite, but the surface area is infinity. So why is that weird? The Panther paradox. So think about this. Usually if you are a painter, we take a can of paint, right? Full of paint. If we take the interior paint inside, it will be a lot more than enough to paint the surface area, to paint the outside. So always do that. Doesn't matter the shape of the container. Take the paint inside will be a lot more than to cover the surface around. But not on this one. On this one, the paint inside is finite, and that is not enough to cover the surface area. So that's why this has the name of the Panther paradox, where we can show that the volume is finite, but the surface area is infinity. So the paint inside is not enough to paint the surface. Therefore, that is the paradox. I put this problem here, but turns out in order to do that, we need calculus 3. So we're going to skip that as well. And with that, we just finished chapter 8. Right. When we go to chapter 10, and we go all the way to 10.4, that's where we have all the material for the second test. So the test will go from 8.4 to 10.4, and should be ready by Wednesday. I'm going to post the review sometime before Wednesday. That's all I can say. But I think that's all for now. We'll pick it up next week. Do you have any question before I end the stream? if you have no questions, so I guess I'll just end the stream here. So I guess have a good weekend. See you on Monday.